Okay, so this is a proton NMR problem, typical of that you might get in the exam. So here we have a molecule, an organic molecule which could be a drug, and a typical question would ask you to detail the diagnostic signals for this proton NMR of this molecule, or to indicate what an NMR would look like. And if you remember from the rules we discussed in lectures, the first thing you need to do is to redraw the molecule. So pretend I've done that now, but include all of the hydrogens on there. So if we go around the molecule, adding hydrogens wherever they have not been explicitly drawn. And remember from what we did last year, carbon can only have 4 bonds, so wherever it doesn't have 4, you make it up to 4 with hydrogen. Okay, so what would the proton NMR of this molecule look like? Well, first of all, we need to distinguish each of the different protons. So for example, we could call them 1, 2, 2, 2 because these are all the same, 3, 3 because those two are the same, 4, 4, 4 because they are the same, 5, 6 and 7. So then in order to answer the question of what the NMR of this would look like, write down the numbers of all the protons that you've identified in the molecule. And then remember, we need to identify 3 things for each peak, or each proton. That is the integration, which refers to the amount of hydrogens at that position, the splitting, which we get from the n plus 1 rule, where n is the number of neighbours on the adjacent carbon, and finally chemical shift. So if we go through each of these in turn, providing these 3 bits of information, we will get full marks for this particular question. So let's look at proton 1. It's adjacent, it's attached to a carbon which is adjacent to a carbonyl. It also has a large number of neighbours. So there are 3 neighbours here, H2, and 2 neighbours here, H3. So first of all, we'll go through the integration for H1. Well, there's only one of them. So therefore, integration is 1 hydrogen, 1 proton. The splitting, well, how many neighbours does it have on adjacent carbons? Well, there is the carbon that the hydrogen itself is attached to. And there is 1 adjacent carbon, and there is a second adjacent carbon. So you have 1, 2, 3, 4, 5 neighbours. So 5 plus 1 is 6, so that will give you a sextet. And then finally, we need the chemical shift. Well, if you look at the correlation tables you've been given in lectures, you'll see that a proton, which is next to a ketone, comes around 2 to 3 ppm. So that's all the information you need to provide to proton 1. If we then move to proton 2, you'll see this time there is 3 of them, and all 3 are identical, they're in the same environment, so therefore we say 3H. But how many neighbours do those 3 protons have? Well, there is the carbon that they're attached to, so on the next carbon there is just 1 neighbour. So 1 plus 1, if n is 1, 1 plus 1 is 2, so therefore it would appear as a doublet. And finally, the chemical shift for a typical methyl group attached to carbon is about 1 ppm. And again, that can be found on the correlation charts. Moving on to protons at position 3, well, this time there are 2 of them, so straight away you can say that the integration is 2H. The splitting this time, well, there is the carbon that the hydrogens are on. The next carbon only has 1 proton on it, so therefore 1 plus 1 is 2. So this will also be a doublet. And because the carbon that these 2 hydrogens are attached to is directly bound to this oxygen, the oxygen withdraws electrons, and these are slightly further, what we call downfield, or higher number on the chemical shift range. So this CH2 will be around 3 to 4 ppm. Moving on to the protons at position 4. Well, here again we have 3 of them. It's a methyl group. They're all identical. So you have 3H. The splitting this time, well, here is the carbon. On the adjacent atom there is a hydrogen, but I told you in lectures that for the purposes of this course we're going to ignore splitting or coupling to hydrogens other than those on carbon. So for all intents and purposes for this question there are no neighbours. So 0 plus 1 is 1, so it would appear as a singlet. And in a similar position, or similar case that we had with H3, the hydrogens are attached to a carbon which is directly attached to nitrogen. Now, because nitrogen is less electronegative than oxygen, it withdraws electrons but not quite as much. So we're not quite as high up as 3 to 4, but we're more around 2.5 to 3 maybe ppm for a methyl group attached to nitrogen. The nitrogen proton itself would integrate to 1, but we won't discuss the coupling here, and also it has a very broad range, and again we won't discuss the chemical shift. However, remember in lectures I said that if you do a shake with deuterium oxide, then that proton signal for H5 will disappear. So that's one way of identifying which peak that is. Moving on now to proton 6. Okay, this proton is attached to a benzene ring, and if you look at your correlation tables you will see that benzene ring protons come around 7.27, which is the protons of benzene itself. However, we have an amine on here, a chlorine, a ketone and an ether, which are all going to affect the position of these from 7.27, but they will always be around somewhere between 6 and 8. So as long as you put the protons in the right aromatic area, then you'll get benefit of the doubt. So for example, proton 6 here, there is just one of them, so it integrates to 1H. There is a carbon that it's attached to. On the neighbouring carbon there is a proton, but there are no protons on this carbon. So there's only one neighbour, so 1 plus 1 is 2, so that will give you a doublet. And again, if you're just asked for the range, you would put maybe 6 to 8 ppm, something like that. But if you're asked to calculate it, you'll need to use the correlation tables that we discussed in lectures to work out the effect of these different groups in the ortho, meta and para positions. But in this case we're just going to stick to an average range of about 6 to 8. And finally, onto proton 7. There is a carbon that this proton is attached to. There are no neighbouring hydrogens here, but there is one here. So proton 7 is also only 1, so it integrates to 1. It will also be a doublet, and it will be in the same range. It won't be in exactly the same place because its environment is different. It's next to chlorine, whereas proton 6 is next to nitrogen, but it will be roughly in this range of 6 to 8 ppm. And that is how to predict the diagnostic signals in a proton NMR.